Welcome back to another video about projectors on Hilbert space. So now I'm going to talk about some of the properties of the subspace lattice that we're going to relate to projectors in a second. So remember, one of the big differences between Hilbert space theory and finite dimensional vector spaces is that I always have to be worried about this closure operation because of the topology. So if I have a subset of H, I can take the finite linear combinations of the elements of that subset, or the span, but it might not be a subspace because it might not be closed. But I can take the closure, and I'll denote that by Vs. That's the smallest subspace that contains S. So that's sort of the closed linear span of a set. So just keep that in mind. Now, there are two sort of operations I can do to subspaces of a Hilbert space. One of them is intersection. So if I have two subspaces, the intersection is also a subspace. It's closed, because obviously intersections of closed sets are closed, and it's a linear subspace. So I have this subspace. And actually, if I take any arbitrary collection of mi subspaces, then the intersection is a subspace as well, and it's defined as the largest subspace contained in all of the mi's. Similarly, I have a join. This is called the join, and I write it as the V. The join of two subspaces is the largest subspace that contains both M and N. No, excuse me, it's the smallest subspace that contains both M and N. And it's also the closure of the vector sum of M and N. So I can do this also more generally. If I take a bunch of subspaces, I can take the largest subspace, the smallest subspace that contains all of them. That's the join of them all, and it's still a subspace. If my family of subspaces happens to be orthogonal, then the join coincides with the orthogonal direct sum. So that's when M plus N is already closed, and therefore I just get a direct sum. Now, speaking categorically, remember that if I have sub H, this is the poset of subspaces. It's a category because it's a poset, and its arrows are the inclusions. So their inclusions, M is less than or equal to N for two subspaces M and N. And this says that I have products. So products are intersections. And this says that I have arbitrary products. And then coproducts are joins. And this says that I have arbitrary joins. So what I'm saying is that sub H has products and coproducts. And yeah, that's what I'm saying categorically. So what I'm actually saying is categorically that sub H is a complete and co-complete lattice. In lattice theory, they just call this a complete lattice, but they mean that it has all set, index, limits, and co-limits. You can also see this, by the way, because it has pairs of products and coproducts. So if you just define these, and then notice that sub H has a terminal object, namely H itself, and it has an initial object, 0, well, then I can see that it's complete and co-complete as well. But sub H is more than a lattice. It's what's called an orthomodular lattice. And that means that I have an extra sort of complementation operation in the sense of Boolean algebra a little bit. So I have an orthogonal complement that's a functor from sub H to sub H op. And this is the property that it's a functor, contravariant. So if M is contained in N, then M perp contains N perp. And then it's also sort of idempotent in the sense that if I do the perpendicular complement twice, I just get that subspace back. And then these are properties that we recognize from everywhere. The join of M and its orthogonal complement is H, the terminal object. This happens to also be the direct sum because this is an orthogonal family. And then the meet, or the intersection of M and M complement is 0, the initial object. There's some other properties. There's the adsorption laws, which are, these are some properties of just a lattice. So this is just some properties of being a lattice. I have De Morgan's laws. So De Morgan's laws hold for orthogonal complement and joins and meets. And then I have this other mysterious law, the orthomodular law. It says that if M is contained in N, then N is M join M complement intersect N. So I'm not going to prove any of these except for this one. I think I'll prove the orthomodular law just for fun, because it's really quick. So proof of the orthomodular law is that if I suppose that M is contained in N, then M complement intersect N, which is the thing that appears here. This is like the complement of M inside N. And I want to show that it's perpendicular to M, but obviously it is because every vector in here is in M complement. So this thing is perpendicular to M. And then also, if I have an N in N, then I can take the projector onto M and apply it to N, and that's something that's in M. And then furthermore, if I take N minus the projector, this is something that's orthogonal, because projectors are orthogonal in Hilbert space. This is in M complement, because it's in the orthogonal complement of the projector space. And it's also in N, because it's a sum of two things in N. So what I've shown is that every N can be written as proj M N plus N minus proj M N. This is the same trick that we used before, where this thing is in M, and this thing is in M per intersect N. So this shows that N is the orthogonal direct sum of M with M per intersect N. And this is the meet. Or, excuse me, this is the join. I keep messing this up because I'm not good at lattice theory. Okay, so this is the join. That's the orthomodular law. I want to make a couple remarks also just to avoid confusion. These laws look a lot like some laws for Boolean algebra, right? In particular, a Boolean algebra is an algebra with like this complement operation. It's like a lattice with a complement, but there's some key differences. And one of them is I have the orthomodular law instead of something like a distributive law. So be careful that sub H is not a Boolean algebra. And in particular, it's not distributive. So it's not a distributive lattice. So meets and joins do not distribute over each other. And this is one of the key differences between classical logic and quantum logic, is this structure of the subspace lattice. It's very different than the Boolean algebra structure of truth values. What the name, by the way, for this like structure is that it's a complete orthomodular lattice. So complete is the lattice theorist way of saying complete and co-complete as a category, and then orthomodular means that it's a lattice, so it satisfies this, and then it satisfies this, and the orthocomplementation satisfies all of these properties. So this is just like a way of collecting all of the things I just said about sub H into like a concise statement that you could look on Wikipedia. Now let's get back to projectors for a minute. We almost proved this exact thing last time, but let me just sort of refresh your memory of projectors since we're about to hop back into them. If P is a projection onto M, then 1 minus P is a projection onto M complement. I can prove this really quick, because now I know a projector is an idempotent Hermitian operator. So since P is idempotent, 1 minus P squared, which is 1 squared, minus 1p minus p1 plus p squared is equal to 1 minus p. So 1 minus p is idempotent. And then similarly, 1 minus p dagger, or adjoint, is equal to 1 adjoint minus p adjoint, but p was self-adjoint, so this is 1 minus p, and I'll obviously 1 is self-adjoint. So 1 minus p is idempotent and Hermitian, and therefore it's a projector, and it's a projector onto its image, and we know that the image of 1 minus p is the kernel of p, and since p is a projector onto M, the kernel of p is M complement. That's all stuff from the last video. Now I'll leave you with this last theorem. So the last theorem says if I have two projectors, a projector onto M and a projector onto N, then I have a bunch of equivalent statements. So statement 1 is that M is perpendicular to N, and statement 2 is that PQ is 0. So this is sort of saying that I can define projectors as being orthogonal when their composition is 0. So let's prove this theorem. Let's prove that A implies B. So if M is perpendicular to N, then N is at least contained in M orthogonal complement. But then if QX, well, every QX is in N, because Q is a projector onto N, so P of QX is 0, because N is contained in M orthogonal complement, which is the kernel of P. So this implies that PQ is 0. And then since the image of Q is equal to N itself, this also implies that P of N is 0. And since P of N is 0, and the kernel of P is M orthogonal complement, this means that M orthogonal complement must at least contain N, which means that M is perpendicular to N. So in our theorem, we've just shown that A implies B, and that B implies D, and then that D implies A. And then I'll have you notice really fast that if I were just to have started here and said M is perpendicular to N, then this implies that M complement is contained, that M is contained in N complement. Then I would have just done this exact same proof, replacing P by Q and M by N, and I would have shown the rest of the things. So that tells me that B is equivalent to C, and that D is equivalent to E by symmetry. So these are by symmetry. And I believe this is a complete thing. I can go from A to B to C. How do I get from C to D? Oh, I can go like that to D, and then from D to E, and then from E to A. So yes, these are all equivalent, and the proof is done.